So we move on in our stats and probability unit, and we actually take a look today at probability. We'll use some of the things that we've learned in our permutations and combinations sections and bring in some things that you might remember from middle school as well. This is one of the more important concepts, really, that you leave out of high school with, that you end up applying in life almost no matter what you do. You look around us, and we've built entire cities as far as economy on probability, and entire industries that rely on the fact that you leave out of high school being really bad at math. So my hope for you is that you won't be one of those customers who doesn't know a bad bet when you see it. So a couple of key terms. The first is outcome, which is a possible result of an experiment. If we have a set of outcomes, we consider that an event, and that's a subset of the entire sample space. So just a reminder on probability, if we can count the number of possible outcomes, if all those outcomes occur at random and all the outcomes are equally likely, if all three of those things are in place, then we can do something called calculating theoretical probability of an event. And that is the number of outcomes of the desired event, which our graphic calls event A, the thing that we're trying to get probability on, and we're going to divide that by the total number of outcomes. So a lot of times when we talk about theoretical probability, we just call that probability. So looking at the graphic, there's 3 things which fall within event A out of 10 total possible outcomes. So our probability of the event A is 3 out of 10. Now the probability can range anywhere from 0 on up to 1, and it tells how likely an event is to occur. So if the event must occur, it's what we call a certain event, and its probability is 1. If an event cannot occur, which we call an impossible event, its probability is 0. Such as, what's the probability of rolling a 7 on a 6-sided die? Well, the numbers available are 1, 2, 3, 4, 5, and 6. There is no 7, so there are 0 outcomes in which 7 happens, so 0 over 6, we reduce that to 0. And speaking of, the probability is expressed either as a fraction, as a decimal, or as a percent. So let's have you try a couple. The probability of drawing an 8 from a standard deck of playing cards. So one of the things we want to think about is what we've been talking about these last handful of days. When we think about a deck of playing cards, how many are in the deck? So there's a total of 52. So our probability is the number of desired outcomes, which is drawing an 8, and the possible outcomes is all cards, which is 52. So how many 8s are there? There's 4 suits. Each one has an 8, so there's 4 cards which are 8s, and 52 total cards. And so now we can reduce that fraction. So 4 and 52 each divide by 4. So our probability of drawing an 8 from a standard deck of playing cards is 1 out of 13. What about the probability of drawing a red king? Well, again, we ask ourselves, how many red kings are there? Well, how many suits are red? There's hearts and there's diamonds. So there's 2 red kings in the deck of 52 cards. So our probability 2 over 52, and when we reduce that down, we find that the probability of drawing a red king is 1 over 26. Let's look at a slightly different type of problem. Let's roll in some of the things we've learned about permutations. If 8 horses begin a race, what's the probability that you correctly predict the finishing order of the first 3 horses to cross the finish line? All right, so when we look at this, let's start from the bottom up. How many possible outcomes are there? Well, how many different ways can 3 horses cross the finish line? So that's a permutation problem. How many different ways can we draw 3 things from a group of 8 in order? And when we've done this in the past, we found out that that is 8 times 7 times 6, which is 336. So there's 336 possible outcomes, and you're going to select one of them. So your probability of correctly predicting the outcome of that race first, second, and third horses in position is 1 out of 336. So let's move forward. It's not always possible to correctly be able to describe the theoretical probability of an event. We may not be able to look at all possible outcomes or maybe count the outcomes. And so in that case, we can look at an event's history, in which we call the experimental probability of an event. So as an example, well, let's look at a definition first. For a given number of trials of an experiment, experimental probability of an event is the number of trials where that event happens, divided by the total number of trials. So let's look at an example from a table. This is civilian workers by job category in the United States. It's a little bit older survey. It goes back to 2005. And so if we were selecting a worker at random, what would be the probability that they would work in that given job category? And there's 3 of these. And I'll do the first one, and then you can try 2 of them on your own. So the first one is, what's the probability that a worker works in sales or an office position? So how many are there from the table? 36 million. Okay. How many total employees were surveyed? And so to get that, we're going to go right down the line and take out your calculator and add up all those numbers. So 49.2 plus 36 plus 23.1 plus 18 plus 15.3, we have 141.6 million. So now we go and divide that result. 36 divided by 141.6. And we end up on our calculator with 0.254 and some more places. We're going to express this as a percentage. So about a 25.4% chance that a person selected at random from this survey works in sales or office. So now that you see how this is done, you try number 40 and 41, come back and check your answers. So hopefully you had a chance to look over these problems. For number 40, resources, construction, and maintenance, if you go to the table, there were 15.3 million workers employed in that field out of the 141.6, which is 10.8%. So the likelihood would be 10.8% probability of selecting a worker at random that he was employed in that field. The next one is somewhat interesting, not managerial or professional. And a little bit later on, we'll find a different way to express this. But for right now, that just means that we're going to add up everything except the managerial and professional fields. So 36 plus 23.1 plus 18 plus 15.3. And if you add those, you get a total of 92.4. We're going to divide that by 141.6. And we get a percentage of 65.3. So a 65.3% chance that a worker selected at random would work in one of those fields. And once we start to think about experimental probability, we can expand that out. Probabilities based on ratios of lengths or areas or volumes, which are known collectively as geometric probabilities. So thinking about an arrow target. Shooting an arrow at a target whose diameter is 40 inches, and the bullseye, the yellow dot in the middle, 8 inches in diameter. So if the area was equally likely to land anywhere, what is the probability it hits the bullseye? So the probability of a bullseye, we need the area of the bull divided by the area of the target. So let's go back and think to ourselves, what is the formula for area of a circle? So pi times the radius squared, pi times the radius squared, right? And so the radius of the bullseye, it has an 8-inch diameter, so that's 4. And then the entire target has a diameter of 40, so its area is going to be 20. So now we have 16 pi, 4 squared is 16, divided by 400 pi. Pi's will cancel, and so to get this value I can go 16 divided by 400, and when we divide that we get 4 hundredths, 0.04, which is equal to 4%. So a 4% probability of hitting the bullseye. So those are some different ways that we can put a number on probability, both theoretical and experimental. Let's go ahead and cement our thinking. Flip to the back page and write down 3 things that you learned today, 2 things that you thought were interesting that you want to know more about, and 1 big question that you still have.